Hello students, welcome back. Previously we discussed polynomial and rational functions. Now let's go to exponential and logarithmic functions. First, the exponential function, which is in general defined like this: a to the x power, where a is strictly positive. But there's a bit of a problem here. What do you mean by x power when x is a real number? Well, that's a little bit difficult to see, so let's begin with easier cases first. When x is a whole number, 0, 1, 2, 3, and so on. In that case, we cannot define it as a repeated multiplication. When x is 0, then no multiplication, so stays at 1. If x is, say, 4, then multiply a 4 times to 1. Now, what if x is negative? Then we get repeated division. So, we covered all the integers. 0 or positive, repeated multiplication. Negative, then we have repeated division. Alright, now what if we have a rational number? In that case, we can re-express it as m over n, and denominator is positive. So whenever we have negative, then you can absorb that negative to the numerator. And we can define it like this: nth radical of a to the m power. Now a to the m power, if m is positive, you can define it like this by repeated multiplication. When that's negative, you can define it like this: repeated division. So a to the mth power is okay. And then once that is done, we consider the nth radical. Nth radical, what is it? Y value, so that y to the n power is a to the m power. Alright, so we have the rational power, and we have this kind of visualization. Of course, I did not plot all the rational numbers here, only selected rational numbers. Here, a is negative 1.88618. It's kind of randomized. And then plotted from negative 5 to positive 5 with this condition. So between negative 50 and positive 50, that's the numerator. So we have 100 points here. 101 points, excuse me, including 0. So yeah. And then if you increase the number of dots, say for example, yeah, let's go to the increment of 0.05. Well, okay, all right, kind of like this. And then, of course, now I'm going from like this. Yeah, okay, all right, that's right. So from negative 5 to positive 5 stays the same, and then we are putting now 200 dots here. 201 dots, excuse me, including 0. And then we have more dots, so filled out more. And of course, that's not the end of it. We can put more and more and more. And eventually, if you go to arbitrary real number, then we are going to be able to complete it. Eventually, we are going to end up with this kind of continuous curve. And that is the general exponential function. We are looking at blue, 1.5 to the x power, red, 2 to the x power, and green, 3 to the x power. And as you can see, the higher the base, the more quickly it grows. So green is above red, and red is above blue for positive side. And to the left-hand side is the other way around, because we're going backward. Now that's when a is greater than 1. What if a is less than 1? We're going to get this kind of graph. 2/3 to the x power, 1/2 to the x power, 1/3 to the x power, like this. And we don't have to consider less than 0 cases, because base always has to be greater than 0. Here, I'm multiplying something less than 1 repeatedly, so as x gets larger, going down. Previously, something greater than 0 is multiplied repeatedly, so going up to infinity. But do you see any pattern here? Looks like they are symmetric, and indeed they are. Why are they symmetric? Well, look at the bases. Take the reciprocal, and reciprocal. You see, 2/3 becomes 3 halves. 1/2 becomes 2, 1/3 becomes 3, and vice versa. Or we can rewrite like these. Same base with negative x powers. And x becoming negative x, what is it? That's a reflection with respect to the y-axis, and that's precisely what we are looking at here. So what's the moral of the story? We don't really have to study this part. Or these, the right-hand side, totally unnecessary, because we can do this, and then at the very last moment, flip, and then we get this. So there's no reason for us to study any of these. In any case, all these properties must hold. Domain is negative infinity to positive infinity. Yes, we define this to all real numbers by completing all the rational numbers. Range is, for that purpose, let me bring back all those pictures. We're looking at repeated multiplications or repeated divisions of positive numbers, so everything must stay positive. So this or that, they're all above the x-axis. That's what we're looking at here. The range is that. Y-intercept is 1, so a to the 0 power is always 1. Yeah, a to the 0 power is always 1 because, no, not here, from there. If I do not multiply anything, then none of these, and we just have 1. So that's a to the 0 power. So no matter what curve we have, they all go through 0, 1. Those are common properties. Now, speaking of 1, there's another thing that you may want to remember. 1 to the x power is always 1 because, you see, 1 to the x power, what is it? Repeated multiplication of 1 or repeated division by 1 will stay at 1. And by the way, a equal to 0 or negative, we do not consider any of those. Of course, repeated division of 0 doesn't make any sense. So you can think of it like that too. Among those exponentials, there's a particularly important base called natural exponential function or natural base or Euler number. It has many names, and it's this number, 2.718 something, and it's an irrational number with no apparent pattern, and it has many properties including these, but in any case, and this is a feature, at 0, 1, the slope of the tangent line here is 1. If you compare that with other exponential functions, you see at 1, stiffer for 3 to the x power green, and flatter for 3/2 to the x power blue, and somewhere in the middle for red. And E is between red and green, actually, 2.718 something. And that's the place where the slope is precisely 1 here. The logarithmic functions are their inverse functions. So f of x is a to the x power. Consider the inverse function. Just go backward. So domain becomes range, range becomes domain. We have flip-flop. And then we have cancellation. It's inverse procedure, so f and f inverse just cancel each other out. So we have x back in. And another property that is a little bit harder to see is this. a to the 0 power is 1. Okay, I didn't multiply anything to 1. So no multiplication whatsoever to 1, so it stays 1. Now, how do I see that? Log a of 1 is same as log a of a to the 0 power, and you see these two cancel out, log and exponential, so the log of 1 is 0. Graphs of logarithmic functions look kind of like these. When a is greater than 1, typical case, we have exponential function like this and logarithmic function like that. This program is randomized, so you can run it again. You may get different graphs, but in any case, you have to have symmetry. Oh, this was really exceptional case. And why symmetry? Well, it's an inverse function, so x is going to y is going to x. That's the nature of the inverse function. Now, if you look at this dotted line, diagonal line, and fold it over, what do you see? X-axis is going to the y-axis, and y-axis is going to x-axis, vice versa. So this folding over is precisely the same action as taking the inverse. That's why we are getting this symmetry with respect to this diagonal. By the way, these are the graphs when a is less than 1, but as I said before, we hardly consider any of these because it's totally unnecessary to consider any of these because all you have to do is consider the standard case and then flip over. The most important case is the natural logarithm when the base a is equal to a mysterious real number e, Euler number, and 2.718 something like that. Actually, this is not precise. You need this ... Oh, I did use weakly equality signs, so that was okay in any case. And this is a rational number with no apparent pattern. And then in that case, y equals to e to the x power is like this. And then right here we have a tangent line, and that has slope 1. And then we have its inverse function. And right here at 1, 0 at the x-axis, we have a tangent line, and that too has slope 1. Okay, so much for natural exponential and natural logarithmic function. As for more properties of exponential and logarithm, well, we'll discuss all those as a part of lesson 9 or as a prerequisite for lesson 9, because until then, we don't really need exponential and logarithmic modeling. We just need to use those expressions for various computations, and that's about it. So as for library of functions, about this much is sufficient, and we're going to just move on.